In this video, we are going to work to classify critical points and also find inflection points for a function. The function that we're going to be working with for this example is the following. So we have g of t is equal to t to the fifth minus 5t to the fourth plus 8. Okay, so our first question here is we want to identify the critical points of the function and then classify them. So whenever we want to find the critical points, the first thing we're going to do is we are going to first compute the first derivative. So in this case, it is 5t to the fourth minus 20t cubed, and then plus 0 from this constant term. So I'm not even going to write it down. And then what do we look for? We look for where does the derivative equal 0, or where is the derivative undefined, or where does this not exist? In this case, since our derivative is a polynomial, we won't actually have this second case here, so we don't actually have to worry about places where the derivative does not exist. So the only type of critical point that we'll have for this function is one where the derivative is equal to 0. Before I set this derivative equal to 0, I want to start by factoring it. So I can factor out a 5 from both terms, and I can also factor out t to the third. And so I'll have 5t to the third times t minus 4. I now set this equal to 0, and now that it's nicely factored, I can see that I have two values of t that give me a critical point. And so the first one is when t is equal to 0, and the second one, which I get from the second factor, is where t is equal to 4. All right, so now that I have my values of t, I can work to classify them. And the way that I'm going to classify them is to use what's called the first derivative test. We could also use the second derivative test, but I am a big fan of the first derivative test. And so what I'm going to do is I'm going to set up a table of values. So I want a table of values where I'm looking at values of my derivative function. And I want to look at what's happening to the derivative to the left and to the right of my critical points. So I'm going to start by just putting in my critical points, leaving space for numbers before and after them. I know that at those critical points, my derivative is 0, so I'll start by filling in those values. And now I just need to pick any numbers in these intervals here. And the reason is that the only place that the derivative is going to change sign is at the critical points. And so it doesn't matter what value of t I choose before and after those critical points. So I usually like to choose some easy numbers to work with. So let's use -1, let's use 2, and let's use 5. You might choose different values, but you should still end up with the same general idea, and all we really care about is the derivative positive or is it negative? Okay, and so to fill in these details, what I'm going to do is I'm going to take these values of t and substitute them into the equation for the derivative. One option we have is to actually use this nicely factored version here, and the reason that's nice is because it's a lot easier to keep track of or to identify whether or not the derivative is positive or negative. So let's go ahead and start with t equals -1. So at t equals -1, we'll have 5 times -1 cubed times -1 minus 4. I could calculate this, but let's just keep track of if it's positive or negative. So we'll have a -1 cubed, which is negative, times a -5 here. And so overall, the derivative will be positive there. So this tells us now that before our critical point at t equals 0, the function is increasing. So this is potentially going to be a local maximum, but in order to determine that, we need to see what's happening to the right of this value. Okay, so when t is equal to 2, we will have, so if I substitute t into my equation here, I will have a positive value times a negative value. So overall, we'll have a negative value. And so this does actually tell us what I was suspecting was true, which is that our function is increasing up until we get to 0 and then decreasing. And so we do have a local maximum at t equals 0. All right, so we just have one more step left to classify our second critical point. We already know that our function is decreasing before this point. So let's see what happens after this point. So when t is equal to 5, we will have a positive value for the first factor and a positive value for the second factor. So we'll have positive times positive. So overall we get a positive. And so in this case, we again have a local extreme value. And so we will have, so our function is decreasing where the derivative is negative, and then it's increasing. So it will have some sort of shape like this. And so at this critical point here, we will have a local minimum. Okay, so let's just write out what our final answer for this is to classify. So we have a local minimum at t equals 4, and we have a local maximum at the other critical point, which was t equals 0. Okay, one nice thing about getting this information is that now we have some idea of the shape of the graph. And so we'll get more specific with this later, but it looks like, so our function should be coming up to some peak here, then going down to some valley, and then increasing again. So just for a sketch of what this would look like, and we'll get more precise, we should see something like this. Okay, so again, this is our local maximum at t equals 0. Here's our local minimum at t equals 4. Okay, now that we have this table set up, we can also answer the second question. I'll just scroll down a little bit. Our second question is asking us to determine the intervals on which the function is increasing and decreasing. So using our table from the first derivative test, we can see where it's increasing. So it's increasing all the way up until we reach the first critical point at t equals 0. So let's go ahead and start listing that interval. So when I say that, so I say all the way up until we reach t equals 0. And so what that means is it is increasing from negative infinity to 0. I'm using open parentheses here instead of closed parentheses or brackets because I don't want to include the endpoints in my interval. So it's only increasing until it reaches 0, but it's not increasing at 0. That's where we have our peak. So you can think of that as the top of the roller coaster before we go down and start decreasing again. The other interval where it's increasing is after our second critical point. So at t equals 4, it's not increasing, but after that it is. And so our second interval will be from 4 to positive infinity. And again, I'm using open parentheses here instead of brackets because I do not want to include my endpoints. So now for the decreasing, the interval where our function is decreasing, that's just going to be in between our two critical points. And so again, I don't want to include my endpoints, and so I'll just write my interval as the open interval from 0 to 4. Okay, and just since this actually looks like the coordinates for a point, let's specify that this is actually, so this is in between the critical points. One of the most important things we need to do as mathematicians is we need to make sure that we're communicating our ideas very clearly. And so in this case, there's some ambiguity because I'm just writing 0, 4. We also use that notation to denote just a single point. And so I find it helpful to clarify what I mean here by writing it out in words. All right, so let's scroll up and let's make sure that we've answered everything that we need to answer so far. So in the first question, we found the critical points and we classified them. In the second question, we determine the intervals on which the function is increasing and where it's decreasing. And so now our third question here is we want to determine the inflection points of the function and the intervals on which the function is concave up and concave down. Based on our sketch that we drew before, just using the first derivative, we have some idea of where it's concave up and concave down, but we don't actually know yet where it makes the switch. So it should be somewhere between our two critical points, but we can't tell just by looking at the graph. The second derivative, the inflection points are much more subtle than the critical points. Okay, so in order to get the precise location, we want to use the second derivative. So the inflection points are where the second derivative is equal to 0. Okay, so let's start on a new page here. And so let me just remind us, what are we doing? We are finding the inflection points. And our first criteria is we want to know where does the second derivative equal 0. We also need to make sure, so inflection points, that's where the concavity changes. And so we first find where the derivative is 0 and then look for sign changes for the second derivative. Okay, so our second derivative here, so let's look back at our first derivative. So I'm going to scroll up. So we want the derivative, our derivative, we will just use the power rule on both of these terms. So we'll have 20t cubed from the first term minus 60t squared from the second term. Okay, so let me write that out. So we'll have, 20t cubed minus 60t squared. So just like the previous work, we want to set this equal to 0. I'm going to first do some factoring. So I can factor a 20 and I can factor a t squared for my two terms. And then I'll be left with t minus 3. And so when I set this equal to 0, now I can easily see what my potential inflection points are. So they're going to be at t equals 0 and t equals 3. And I'm writing potential inflection points because we don't actually know yet where the sign changes are. Based on the sketch of our graph and what we know about the critical points, we can make a guess that t equals 3 is the only actual inflection point. But let's get more precise with this just to be sure. And also just because for some other problems that you might work on, it might be more difficult to determine whether or not a point is actually an inflection point just by guessing, or just by guessing on the shape of the graph. So what we'll do is, again, let's set up a table of values, because what are we doing? We are looking for sign changes, and so this is very similar to what we did with the first derivative test. We are looking to see where does our second derivative now switch from positive to negative or negative to positive. So again, let's just choose some values of t. So I chose -1, +1, and I chose 5. You might choose different ones, but we should end up with the same signs in our table. Okay, and so now we are plugging these values into the second derivative. I'm again going to use the nicely factored version. And the reason is that I can easily just keep track of if something is positive or negative using this nicely factored version. You could go back to the original version, plug the values of t in, get the exact number, and then you would still get the correct answer because you would still be able to keep track of whether or not you were getting something positive or negative. All right, so when I plug in -1 to this nicely factored version, I'll have a -1 squared, which is positive from my first term. And then my second term, -1 minus 3, I'll have a negative. And so overall, my second derivative in this interval is negative. When I plug in +1, again, my first term is positive, and my second term is still negative. 1 minus 3 is negative. And so my second derivative here is going to be negative. So in between these two potential inflection points, the second derivative is negative. Now at 5, we finally get a flip because here the first term will be positive and the second term will also be positive. So we have positive times a positive, which is positive. And so we see now, so in the previous step we had our potential inflection points. We now see exactly where the sign changes, so it only changes at t equals 3. And so we get an inflection point at t equals 3. And then using what's in our table, we can also write what the intervals of concavity are. And so remember, if the second derivative is negative, the original function is concave down. If the second derivative is positive, then the original function is concave up. And so let's start with concave up. So our original function is concave up anytime after 3. So at 3, at t equals 3, the second derivative is 0, but then at any value of t after that is going to be concave up. And so our interval will be from 3 to positive infinity. And I'm not including 3 because there the derivative is equal to 0. For where the function is concave down, we have to be a little bit careful. So we have this sort of dividing point here at t equals 0. The second derivative there is 0. And so I'm going to split this into two pieces. So I'll have from negative infinity to 0, and then from 0 to 3. And again, I'm not including my endpoints because in particular at 0 and 3, the second derivative is 0. All right, and then let's just have, one thing I like to do is I always like to imagine what does this tell me about the shape of the graph. And so one way that you can remember this is if it's concave up, it looks like a cup. So I should have something like that. And where it's concave down, it looks like a frown. So we should have something like that. And then I often just put in two little dots for eyes so that it actually does look like a frown. Okay, so let's just go back to the first page, double check that we have answered all of the questions. Great, so we determined the inflection points, and then we also determined the intervals on which the function is concave up and concave down. Now let's actually look at the graph of this function. So we had our sketch from before. We know some things about where it's increasing and decreasing, where it's concave up and concave down. So now let's compare that to what is really happening. So here's the graph of our function, which I created on desmos.com. And we can see that, yes, we do have a local maximum at t equals 0. We do have a local minimum at t equals 4. Again, even looking at the exact graph, so a precise graph of the function, it is hard to see where the inflection point is. We know that it's somewhere in this general region because to the left of that, it's concave down, looks like a frown. And to the right of that, it's concave up, looks like a cup. We know from our calculations that the exact point at which it switches is at t equals 3, which is right here.